Hello, welcome back. First of all, congratulations and congrats for finishing the assignment. That's the main important thing. Whether you correctly finished the entire assignment and got accurate motion stability measures, or whether you didn't really get an accurate understanding, but you finalize and finish the assignment. That's the main thing. As long as you're getting comfortable with Visual 3D coding and getting into higher and more complicated biomechanical models, that's the main important thing. So for that, congrats. All right. So first of all, we'll start with the motion stability assignment. Okay. So before we start any analysis, you have to first create tags for um, trials that are walking for the participants that are walking on north or walking south. It depends on really your orientation, your lab orientation, and the data you're working with. In our lab right here, the main gate lab was actually built within the biomechanics research building here at UNO that is either facing north or south. So this specific participant, they're walking south. And when I say south, it's just globally, not really relative to the lab or anything, but relative to the planet. So for this specific trial, they're walking south, and for the other two trials, they're walking north. Now this makes a big difference because when you're calculating the measure stability or basically any other measures, when you're calculating trigonometry, you need to make sure that the coordinate systems that you have are relative to the lab. We'll first start with with trigonometry and all of these models relative to the lab, and then once you feel comfortable, you can start working on um, models that are relative to the virtual lab, like we did in the angular momentum calculations. But when we calculate the motion stability, when we calculate the extrapolated center of mass, so when you see here like this yellow dot, that's the projection of the center of mass. So we basically use this position plus its velocity, taking account the inverted pendulum, so the leg length and the gravitational pull. We calculate the extrapolated center of mass. The extrapolated center of mass might fall like in front of the foot right here. So when you calculate that relative to the base of support, for example, if you look at the center of mass here, you see like everything is relative to the coordinate systems of the lab. So the origin of the lab is where the x, y, and z coordinates there. So when they walk in south, when you look at the y value of the center of mass, they're actually getting closer to the lab origin. So the values are decreasing, and then once they pass the threshold, then the values go to the negative, become negative, and it's the opposite is true for walking north. So when they get closer, they go from negative to positive. So they're actually decreasing until they reach the lab origin and then keep increasing. So that's exactly why we need to run the margin stability calculations based on whether the participant is walking north or walking south. Alright, so the first thing you need to do is create new tags as we've done. I've already did that, so we can go ahead and like for example, let me just delete these and then we create new tags. So we create like walking south, and I'm gonna choose the first one, and then walking north, walking north, and then we'll choose the last two. So now we have that covered. Then we'll go ahead and start working on our pipeline. So I'm just gonna start with the first trial, and because I already have one trial that is walking south, I'm just gonna work on this so you can follow with me, and I'm gonna step each command one by one so you can actually follow as well. But when you have large data, make sure you're like run one trial first, make sure like all the calculations make sense and the pipeline is working fine, and then you can start running your analyses for the entire data set that you have. For example, here we're only working with 3 tries, but we collected 21 younger and 21 older adults, so like 42 in general in total, and we had 3 sessions. In each session we had 12 tries. So like, look at that, that's more than 1200 tries. So you have to make sure that your data is correct before you start running the whole the analysis for the whole data set. And if you remember what I mentioned in the first videos, is that you have to always, and I can't stress this enough, but you have to always check and double check your data to make sure everything is correct and makes sense. Alright, so I'm not gonna run this. I already saved this file. Actually, it's fine, yeah, I already saved it. And then I'm not gonna also run this because when you run like a tag, you can't see the graphs because if you have more than 1 trial, you know. So I'm just gonna, even if you have 1 trial, like for example here, when I run like any of these, it's not gonna give me like values. It will give me the graphs but not the values. So I'm just gonna keep working on this first trial so you can see everything. Okay. So if you remember, the first thing we need to do uh, is get the extrapolated center mass, which is the position of the center mass. The x is the position of the center mass plus its velocity divided by omega, and omega here is the square root of the gravitational pull divided by the length of the leg. And depending on how you want to calculate it, I prefer to calculate it very accurately, so I'll show you my method. But here in their paper, like, they calculated the length of the foot using Winter. If you don't know Winter, like, good luck. But Winter is one of the big names in biomechanics. You should read his book called Biomechanics and Human Movement. Just that's like the basics, you know. You have to know this book. So in this book, and he also, like Hoff and colleagues, they also referenced this paper. I'm not really familiar with this, but what I know is, like, from Winter book, they refer to these lengths. So like, they basically use the sagittal length of the leg by coefficient. So they use these coefficients times the trochanteric height. And in the frontal plane, they use this coefficient. I don't use these. I mean, obviously, you can. It's up to you. But because when we have the data, like I have the data, I go with a more accurate way by calculating the length uh, of the foot by measuring the vector between the center mass here. Like, you see the center mass here, that's like the green ball, and or the green sphere, all the way to the mid distance between the lateral and medial malleolus. Alright, so let's go ahead and get started. So the first thing we need to do is calculate the vector, which is basically just subtracting the proximal end position of the right foot from the center of mass. The proximal end position of the right foot segment, when we go to the kinetic kinematic right here, yeah, like, you can choose the center of gravity, whatever, but the proximal end position, and you can look that up in C motion. They'll tell you it's basically the mid distance between the ankle joint. So which is the how you define it here. We define it in the model, if you remember, as the distance between the lateral and medial malleolus. That's the proximal end. So when you go to like the left foot or right foot, wherever, so you see like proximal position is the left ankle joint center, which that virtual joint right here is the mid distance between the lateral and medial malleolus. So it really depends on you how you want to define it, but make sure you report your results exactly in the publications you're using, or like any publication, whether like that's a journal publication, a peer-reviewed journal publication, or a conference, or like your thesis if you're a student, or anything else you're doing. Okay, so once we get that vector, you do the same thing for the left subtracting that proximal end from the center of mass. Now we have the vector now, but we need to extract the magnitude. So to extract the magnitude, we're just using Pythagorean theory. So the square root of the y of the LLV, the one that we just created, this is gonna be the magnitude of the lag length plus the z. So we're basically taking the length of that segment from the foot to the center of mass, and we're also taking like the AP. So if the center of mass is here, so we're just basically taking this that magnitude, the magnitude of that vector. Okay, so we do that, and then we do the same thing for the right foot, but in terms of the frontal plane, we do the same thing, but we take the x value. So we take like the length, and then we take the x. So like we take this. Let me show you in the video here. So in the frontal plane, we take this distance, like this vector, and then this vector. So the distance between here in the frontal plane, and then in the vertical axis, and then we just measure the Pythagorean, you know. All right, and then the sagittal plane, we do the same thing. So we take this length up until like the ankle, and then we take this length, and then we measure like the Pythagorean, you know, distance, the magnitude, and that's how we get the leg length. So once we get the frontal and sagittal plane leg lengths, we calculate the eigenfrequency omega. So if you remember, the eigenfrequency omega here is the square root of the gravitational pull divided by the leg length. So that's what we're gonna do here. So we take the square root. Also, in any coding language you use, you have to make sure you're using the parentheses correctly. So make sure you do that. So the square root, and then we open parentheses, and then we add the gravitational pull. So 9.81 divided by this magnitude that we just created in here. So you can add x, or you don't need to add x. It just depends on you. Either ways, there is only one column there. So if you go to the sagittal, let me actually just go ahead and run all of these, and then when we go to our derived process, so here we're running like square root of right leg length. So right leg length here, sagittal, right leg length sagittal here, it only has one column, x. So you can either like put x or remove it. It doesn't matter really. I added just in case, you know, but you don't need to. Visual 3D will automatically understand that there's only one column. But if you have more than one column, so if you have like x, y, and z coordinates, then you have to specify the specific column. Okay. So then we do the same thing for the frontal plane. So we have like the omega of the frontal, omega of the sagittal, but obviously we change, you know, the values here. So frontal, just whatever name you named it. I named them like right leg length frontal, right leg length sagittal, and then like left leg length sagittal, and then left leg length frontal. And then I named like left omega frontal, and then left omega sagittal, and so on, you know. Alright, so once we have, now we have, basically we have this, so we have the omega, we have the vertical, we have the omega, we just calculated the omega, and then we have the position of the center of mass. We just need to extract the velocity of the center of mass now. So when you extract the velocity of the center of mass, we just basically use the first derivative. If you go here and like type derivative, it will give you like first and second. So if you want the acceleration, you get the second, and if you want the velocity, you get the first. Alright, so once we have the first derivative, now we have the velocity of the center of mass. If you're using treadmill data, because I have overground data, I don't need to add anything, but if you're using treadmill data, make sure you add the velocity of the treadmill as well to the velocity of the center of mass, because when they walk in the treadmill, they basically walk in the same place, so you're not gonna get velocity of the center of mass. You're probably gonna get like 1.1 meter per second, or like 1 centimeter per second, 10 centimeters per second, you know. So you have to add the velocity of the treadmill to make sure you have accurate data. All right, so once we're done with that, then now we need to calculate the extrapolated center mass. So if you remember, the extrapolated center mass is the position of the center mass plus the velocity of the center mass divided by omega. So that's what we're gonna do here. We'll first calculate the extrapolated center mass of the right leg in the AP direction, the ancestral plane. So here, we're calculating the extrapolated center mass for the right leg in the ancestral plane. So we have the center mass position in the y-axis because ancestral plane, plus then we open brackets, and then we add the velocity of the center mass, and also in the y-axis, so like the ancestral plane, divided by the omega of the right leg in the ancestral plane. Then we get the extrapolated center mass. And we're gonna go do the same thing for the left leg, and then we're gonna do the same thing for the right leg and left leg, but in the frontal plane. So here we just need to change the y for with x for both the center mass position and the velocity, and then we change the omega for the frontal plane. Again, if you notice here, like we have the position of the center mass plus, and then we open brackets, and then in the brackets we divide um, the center mass from we divide center mass and the omega, which is the eigenfrequency. All right, so now we have basically the everything we need. So we have the extrapolated center mass, and then we also have the markers to define the basis support. So now what we need to do is make sure we have correct calculations based on the direction of the motion of the participant. So here, like they're walking south, when we want to calculate the measure stability in the sagittal plane, because we want to make sure that if the extrapolated center mass is within the basis support, we need it to be positive, and if it's outside the basis support, then we need it to be negative. Which means, because when they're walking south, they're getting closer um, to the origin. If the extrapolated center mass is closer to the origin, it's gonna be the value is gonna be lower, and if it's further, it's gonna be higher. So if we want to make sure that the base support of the extrapolated center mass is within the base support and is positive, then we need to subtract basically we calculate like the extrapolated center mass minus the here I chose the heel marker, so minus the heel marker. If it's actually we do the opposite, so like the heel marker minus the extrapolated center mass. So when the heel marker is bigger, so let's say like the heel marker is 1 meter now away from the origin, and the extrapolated center mass is like 0.5 meters. So then we'll have 1 minus 0.5, then it's 0.5. So we know that it's in front of the center, in front of the foot. But if it's behind, it's gonna be negative. So that's what we do here. Because they're walking south, the anterior posterior measure of stability for the right leg is gonna be the right heel marker on the Y minus the um, extrapolated center mass in the AP for the right leg. You can also choose other markers, like you can do the extrapolated center mass between the heel marker and the toe marker to make sure that it's always within those distance. So if you choose to also add here I did not add it. If you choose to like add the toe marker, then flip it. So basically subtract the toe marker from the extrapolated center mass. So then we know if it's in front of the toe marker, then it's negative, and if it's behind it, so if it's within the base support, then it's positive. Okay, so we do the same thing for the left leg as well. So we subtract the extrapolated center mass from the heel. In the medial lateral, it's gonna be also different, because here we're subtracting the right fifth metatarsal in the x-axis from the extrapolated center mass in the x-axis, and that's because when they're walking south, for the right leg here, we have like right leg 0 is here. So um, when it's more like lateral to the origin here, if it's like more, when you're looking at it from this way, if it's more right, then it's gonna be bigger, and if it's closer to the origin, it's gonna be smaller. So when we want to make sure that the center mass is not lateral, the external center mass is not lateral to the foot, we subtract this, the fifth metatarsal here, this one right here, this one. So you see, like I chose the right fifth metatarsal because it's it's the most lateral. It's a little bit even more lateral than the calcaneus right here, and the ankle marker. So I chose that basically to define the edge of the base of support. But you can choose, depending on your marker set, you can choose any marker that defines the boundaries. So here, um, when the center mass, for example, is here, like you see the center mass. If you think, as this is the extrapolated center mass, when it's not lateral, so it's like, let's say this is 10 centimeters and the fifth metatarsal is just 1 millimeter. So like 10 centimeters minus 1 millimeter, that's 9. Um, 10 centimeters minus like 1 centimeter, that's 9 centimeters. So it's within the base support, it's not lateral. But if it's outside, then it's gonna be like let's say it's gonna be like minus 10 from here, minus 10 minus 1, that's gonna be like minus 11. So that's why I said, it does make a big difference whether you're using only south or north. Like, it makes a huge difference. So here for the medial lateral margin stability for the right leg, only for the right leg, we do calculated by adding the center mass, the extrapolated center mass of the right leg and the x axis, but it doesn't matter because that's what we calculated. So either you put x or you don't put x, it doesn't matter. Actually, let me run all of these. So you'll see here the extrapolated center mass of the right leg and the x of the right leg here, you only have one value, which is x. So we subtract that, and then like minus the right fifth metatarsal and the x-axis. But when we do the left leg, we do the opposite. So we first add the left metatarsal, fifth left metatarsal, and then minus the extrapolated center mass, because here is basically the opposite. So now, if the extrapolated center mass is larger than the fifth metatarsal of the left leg, then it's gonna be positive, So then we subtract the left metatarsal from the extrapolated center mass to make sure that we have negative values if it falls outside the base of support. Alright, so once we have those calculations, let's take this. So here I added like a completely new folder called measurement stability. So add all of, oh wait, so what's going on here? So stability center mass. Um, yep. So I probably missed a few steps. I didn't read it, but so if you don't have the actual data you're calling, it's not gonna calculate it. That's why we're missing a few, because I missed a few steps, so it couldn't find the data. So now we have all the data. So now we have our margin stabilities for both the left and right legs in both anterior and both the frontal and sagittal. For example, you see here this is the marginal stability for the left in the AP. So here it's within the base support. It's still positive, it's within the base support. And then now it's actually, it's almost like leaving the base support, so it's probably like around here. So like for example, you see like it's 11.11 meters, so that's 11 centimeters. So it's getting closer to the edge. It's getting close to the edge, and now it's actually falls behind the center, so behind the base support. So it's probably like around here. Let me see the actual values. It's minus 0.03. So the extrapolated center mass is here, but the base support is here. So basically what's happening here is that the base support is moving much faster than the extrapolated center mass, to the point that the base support fell outside the extrapolated center mass, not the opposite. Because they're sliding here, you see like the foot just slides so fast that it actually exceeds the velocity and the speed of the extrapolated center of mass. But then they stop their feet, and then the extrapolated center of mass gets back within the base support. So it makes sense, it's correct. When we look at the lateral, for example, let me see like the lateral. In the lateral, in the frontal plane, they actually did a very good job in controlling their frontal plane, so they always kept it within the base support. But let's see the left. Even the left, they actually did a good job. So yeah, but like obviously, I don't know if you're very familiar with biomechanics and if you're advanced, like if you have a master's or if you have a PhD in biomechanics, like I do, you know that this specific measure, although it is very good, it does have a lot of limitations, like this for example, because they don't take into account the whole like basis support. So like although it's still like it does not exceed the limit of the fifth metatarsal, whether that's for the left or the right leg, it's still within like here. So it probably did, like when you look at here for example, 24 meters for like when it's right here. Let's see, like right here is almost went to the negative, so it almost like left the base support, but it's good. But for example here they basically overcompensated, so the accepted center mass could be somewhere here. Technically it's within the base support, but you know, we can't say for sure because we only compare the extrapolated center of mass in the frontal plane relative to the fifth metatarsal of that leg. That's it. Okay, so now once we have our values, we need to extract the actual marginal stability in certain events. You know, now we have the values, we have all of these like marginal stabilities throughout the whole trial, but we want to extract them on certain locations. So with the marginal stability, you can either calculate the minimum marginal stability during stance when the leg is in contact with the floor, or you can get the marginal stability at heel strike. So here I calculated the global minima of the marginal stability at the stance of the right foot. So the right foot stance in here. So then I named it minimum marginal stability AP for the right leg, derived, and then we use the marginal stability, the one that we just created now, and then you know, you can just put X or whatever, you only have one component, which is X. And then the event sequence I chose from the right heel strike to the right toe off, so like when the foot is on the ground. I did that for the left foot as well, and then for the ML as well. So here we have the sagittal plane, and then we have the frontal plane, still on the stance phase. And also I calculated and then like if you remember, you know, we calculate the events, so we have the events, and then we extract the events by using the command called metric signal value at event. So then we're extracting that at those values, so like at the minimum the minimum measure stability at stance for the right leg and the left leg in the frontal and sagittal plane. So we have that. So you see here, the only difference is here, like is when we change the event name, and also we change the obviously the specific outcome measure that we're using. So we're using here the measure stability of the AP for the right leg, and then we're given the metric name. We're given this metric name. It's basically the same, but you just added the minimum here. And then we're using the event of minimum marginal stability for the right leg. And then we're doing the same thing for the left leg and the sagittal plane, and then we're doing the same thing for the right and left leg in the frontal plane. The next thing, like I mentioned, you can get the marginal stability at heel strike. So that's what we're gonna do here, because we already have the events. We don't need to create more events. So we're just doing the same thing, but we're changing the events to right heel strike, left heel strike, for both the AP and MN, so like both frontal and sagittal planes. And then we're exporting that. So let me actually go ahead and export that here. Walking south. Actually, you know what? You don't necessarily need to do it. Let me just wait. Let me just wait until we finish the walking north, and then we can just extract all of them together. Okay, so I'm just gonna execute this again. I'm not gonna save it because I already did. And then it's just gonna give us an error because the file path is not updated. So here it's gonna say there's no file path, so it doesn't understand that. All right, so I'm gonna you do the same thing for walking north, but you just basically switch the signs. Okay, so then we call the walking north trials, and then the first ones are all the same here. Doesn't matter, but what matters is later on is how you calculate the extrapolated center of mass, how you calculate the margin stability by subtracting the stability center of mass from the specific markers. So here we still calculate those with the same calculations, but then when you start calculating the margin stability here, then things are different. So when we load in the walking north trials, in here when we want to measure the margin stability in the AP for the right leg or for the left leg, whatever, for both are going to be the same, but we're basically using the extrapolated center of mass minus the right heel, because the extrapolated center of mass is going to be larger than the right heel, what is closer to the origin or whatever. Like when we actually plot this in any location, is going to be bigger and larger than the right heel because it's in front of it, when it's in front of it. So if we want to measure whether it's negative when it's outside, then we just use this formula. So we're subtracting the right heel from the extrapolated center of mass, because when it's bigger it's gonna be in front when it's and positive, and when it's negative and smaller it's gonna be behind the right heel. And that's for the AP, for the sagittal plane. So for the frontal plane, it's gonna be obviously different for the right and left leg. So here when it's bigger, it's gonna be positive if we just use that first. So then we use the right heel for the right leg. I mean the right fifth metatarsal for the right leg minus the extrapolated center mass. So when it's positive, it's gonna be within the base support, and when it's negative, it's gonna be outside the base support, so like lateral. And we do the opposite for the left leg. So that's what we do here. Target, process right fifth metatarsal, x minus the extrapolated center mass for the right leg, but then we do the opposite for the left leg. So it's gonna be the extrapolated center mass minus the left metatarsal. And then everything else is gonna be the same. So let me execute it. gonna say override this, and then we finish that. So now when we use all files, and then when we go to the metric here, then we go to margin stability, then we'll have all of our margin stability. So we have the minimum margin stability, the AP, so then we have all of the values, and then if you want you can get the minimum of these minimums. So you see, like, we actually have one that is outside the base support, and that's for the frontal, for the sagittal plane of the left leg. Sagittal plane of the right leg, we also have one minimum here. And then we have the ML, and now it's good to check all of these. Like I said, always check your data. But you see here we have the ML margin stability, ML left heel strike. It's missing the other two, and then margin stability. So the left, both the anterior, both in the frontal and sagittal planes. Oh wait, I got it wrong. So yeah, so the minimum margin stability and the margin stability, both missing here the Vulcan North trial. So why is that? Let's see. When we go back to our code, Vulcan North, this is Vulcan North. Let's look again. It's gonna be the minimum. So we're missing the minimum margin stability for the left leg and the frontal plane. So we have the sagittal plane, we have the right and left, and then we have the minimum margin stability for the frontal plane for the right leg, but we're missing the left leg here. So let's see what's going on. Oh, that's because we're missing the margin stability for the left leg in the frontal plane. So when we go back to our code here, when we're calculating the margin of stability here in the frontal plane for the left leg, we probably have some sort of yep, so here we're missing a null. It should be left leg length. So when I go and step on this and then we run this again, we should have it. Was not created because there was no results. Interesting. So let's go back and investigate what's going on. So here the drive process, extrapolated center of mass, ML left leg length X. Go back to the extrapolated center of mass, ML left length. This right here is the problem. Let's check. And derived extrapolated center mass, ML left length. Yep. Looks like we don't have data here. Extrapolated center mass, left leg. What we do? We do have that for this, and we do have that for that. So this is correct. So we do have this data. Then you go back here. Margin stability, ML length. First of all, this is correct, but maybe we don't have the fifth metatarsal on this specific trial. Let me see. Let's go back and see where is it. We chose the processed. So target processed left fifth metatarsal. We actually do have. We don't. Yeah. So that's the problem. So when we have something like this, I'm gonna go ahead and use the calcaneus instead. So the left first calcaneus, this one right here. So we do have data for that. Sometimes you see here, like, you don't have, sometimes in our collection, because we created a wearable apparatus for sleep and perturbations, it was worn over, you basically wear it on top of your athletic shoes, and sometimes it covers that marker and we end up with no data. It's not a big problem, but you just have to make sure that something like this, like, doesn't happen. So what I'm gonna do here, I'm gonna um, change this to left calcaneus 1, and then I'm just gonna go step on this. I'm just gonna, like, rerun the whole thing. It should be fine. So now when we go back to our minimum, so now we'll have the minimum margin stability for the ML. Oh, we're still missing one. So I have the minimum margin stability ML left, and then we have the margin stability ML left at heel strike. Yeah, that's probably man, like, yeah, okay, we have both, because I was only checking. Yeah, so now we have, because I only had the walking north, but when we choose all of them, we should have it. So now we have all the data. Sounds good. Alright, so now we go back and export our data. I put, like, marginal stability, actually V3D for 1, marginal stability, data. Just put answer here. Alright, I'm gonna step it. Obviously, when you can do it, like, manually, so when you have it all file, it's just gonna export the data for all files. So when we go here, if we do tutorials, and when we go to 400s, you'll see it. So when we open this, now we'll have all of our data in here. But obviously, like if you remember, the first row is gonna be your the whole path for your data. So we have the first trial first, and then we'll have the second trial, and then we'll have the third trial. And then here you're gonna have the name, so we have the margin stability at heel strike, and then we'll have the minimum margin stability for both, like, right, left in the sagittal plane, then right, left in the frontal plane. Alright, that's how you do it. If you have any questions, let me know, but yeah, good luck. And once you finish these assignments, basically the sky is the limit. You can do anything you want. Again, good luck and see ya.